Hello, everyone. In this video, we cover the last part of the notes section for section 1.4, the derivative function. So here we have a summary box with the definition of the derivative function f prime of x. So we saw this in the previous video. You've also seen this in section 1.3 as well, where this x was an a. So here we've just changed the notation. We're using x inside this formula instead of a. And I want to reiterate, mathematically, we use x's to represent a variable, meaning we can change this x. So we could plug in anything there. But just to recall, so that derivative at the point x is equal to the limit as h goes to 0 of the slope of the tangent line through the point x and x plus h. So now let's finish off these notes with our example 2. So for each of the following, you are given the graph of a function f. Your job is to sketch the graph of the derivative. So before I sketch it for you, I want you to try sketching that derivative on your own. What I want you to keep in mind are those 3 observations that we made in the previous videos. Note the derivative will be equal to 0 when f has a horizontal tangent line Also keep in mind that our derivative is bigger than 0 or positive when our function f is increasing. And finally, our derivative is going to be negative or less than 0 when f, our original function, is decreasing. So go ahead and pause the video and try to sketch in those derivatives on your own first. And then when you're ready, keep watching. All right, so I'm going to go ahead and sketch those derivatives, and I'm going to talk out loud while I do it so that you hear how I'm thinking about this problem. So I'm going to draw my derivative for each case by using these observations that we've outlined. So I'm going to start by noting where the derivative is going to be 0. So I look at my original function and I find that I'll have a horizontal tangent line here, here, and here. So my derivative is going to be 0 at those points. It's going to cross that horizontal axis. Okay, so now I'm going to observe what happens in between these zeros. Well, to the left of this 0, my function is decreasing. So that means my derivative is going to be negative. Here, to the right of the 0, my function is increasing. So that means my derivative is going to be somewhere up here in the positive. Now in the next 0, my function's decreasing, so I'm going to be down here. And to the right of the final 0, my function is increasing, so I'm going to be somewhere up here. So I need to be positive here and here, negative here and here. So I'll draw on those signs just so we can see. Negative, positive, negative, positive. And so I'm going to connect these zeros with a curve that's negative, then positive, then negative, then positive. So it should look something like this. Maybe a little more smooth down here. So if you weren't able to draw your own sketch for graphs A and B, I want you to pause the video and now try drawing the graph for B using the thought process we just went through. And when you're ready, go ahead and start the video. Awesome. So this one is a little bit trickier, but it's the same ideas that we can use. First, I'm going to denote horizontal tangent lines. So from here to here on my original graph, my function is just increasing at a constant rate. So the tangent line at any point on this graph is going to be the same. Here, the second part of the graph, I have this smooth curve where I have a horizontal tangent line here. So I know we're going to have a 0 here. To the left of that 0, we're decreasing. So we're going to be negative. And to the right, we're also decreasing. So we're going to be negative again. So over here on our derivative, we're going to be negative and 0. But then over here, what do we notice about that tangent line? Well, all of these tangent lines are going to have some positive slope, but it's going to be the same slope throughout this entire interval. So that derivative is going to look like some straight line, straight constant line like this. But then there's going to be a break in my derivative graph, because down here, right after I get to that break or that corner in my graph, I'm going to immediately get negative. So I'm positive, positive, positive here with the derivative and the slopes. And then right at this point, I'm going to drop negative. So there's actually going to be a break in my derivative graph. But it'll start again here, somewhere negative, hit 0, and then go back negative. So one thing that we can learn from this exercise is that the derivative of a function or of a graph is not always connected. We might have jumps like we see here. But in fact, we know exactly when we have jumps. We're going to have a jump whenever we have a corner in our graph. And that's because if we look at tangent lines to the left and to the right of this corner, their slopes change drastically, as we notice from positive to negative right away. No 0 in between, no horizontal tangent line here. So we're going to have a break from somewhere positive to somewhere negative. So I'm going to clean this up just so you can see that derivative function. And I just want to finish this video with our last bit of notes here on a word about terminology. So if the derivative of a function exists at a point, then we say that the function is differentiable at that point. If the function has a derivative at every point, so for example, this graph, there's no derivative right here. We don't know what this is. There's no tangent line at this corner. Then we'd say this function is not differentiable at that point. So I'll write that down here. So if the derivative of a function exists at a point, then we say it is differentiable. If it does not, then we say the function. So I'll say the function rather than it. And we say the function is not differentiable at that point. Awesome. Well, thank you for listening, everyone. Feel free to rewatch this video to help get more practice on these concepts. Thanks for watching.